Hey there, welcome. This will be a longer video, I suppose, and it also will be a little bit more relaxed and I think maybe a little bit more filled with errors, because it's rather a session I'm doing here than it is a video I planned before recording. So, yeah, the reason I wanted to do such a video is that I want to just show you a workflow, how I record my scripts, how I solve a automation problem. But it will be really basic, so it's nothing fancy, but you can see the workflow and you can see me how I navigate between the tools. So, alright, let's first show you what I wanted to do. So, a whiteboard here, and let's say you have a problem. You have a problem with Microsoft Whiteboard. Yeah, you have a problem which is similar to this. You have a beam which is between two constraints. What's the English word for lager? Well, bearing. Yeah, bearing. So you have two bearings. One is a fixed bearing, one is a loose bearing. And so this can move in this direction. And you see the moments are not coupled, so they're not fixed. So, for example, you have a beam which is fixated in a wall here. You can press down here and transfer a moment or torque on this point. You cannot do this with those bearings. So this is free to flex, just like this, for example. You see that the turning here will not introduce any force reaction. So just translational force transmission on these bearings, right? Okay, so we have this set up more or less, and I thought it would be cool if you just had the option. Oh, okay, I didn't want to do this. This with a red color. If you have the option to separate the length and maybe also the diameter, well, I should say that I wanted to do a round section, a cross section, where you can specify the diameter and also the length. So those two are the input variables. I think we will fixate it to be steel from the material properties, but we could change that as well, right? And what we wanted to do is to just look what happens if we just put a force on the middle, right? Like this. And yeah, we can do all sorts of things. So for example, also to do the position of the force, right? So this parameter A. Is this half the length? Is it more or less? This can also be input parameters, but let's start simple. Let's make it just that it is fixed with A. And as my boss already told me a couple of times, and it's rather important that you know that as well, we only believe what we understand and what we can see. So it's always important to have your finite element modeling checked by a hand calc. And so I prepared something in advance. You can find the analytical equations on different sites in the internet. So this is rather easy to find and prepare it in advance. So you can see it right here. So Excel file which I prepared, where you have it's in German. I'm sorry about that, but you can see the terms. You have something like this. And here's a source if anyone wants to check that. So it's not my own doing here, because yeah, I found that on the internet, and why not include that? Why do it yourself? It doesn't make sense. So it is here. You have your force reactions, and you have also your maximal displacement in the whole section, in the whole beam. And I have prepared it something here, the hand calc, so you have a diameter of auto diameter, and also these orange colored things, those are input parameters. You have a density, which is in this case steel. You have a length of the beam, which is the total length, indicated by the L here. Then the mass can be calculated by calculating the surface area, which is diameter squared times pi divided by 4. So this is the area in square millimeters, times the length, which gets you the volume. So surface area times length is the volume, and volume times density will give you the mass. So the mass in tons is this value, and you also have your properties of the moments of inertia. Yeah, I think that's alright. Yeah, moments of inertia. Which you can look it up. For a round section, it's P d to the power of 4 divided by 64. And yeah, so this will be important later. So the force is calculated by just multiplying the mass by that value. So in this case, we want to simulate the Eigengewicht, so the mass of the beam, yeah, so the own mass of the beam. But I know it's not perfect because the mass is distributed, but it's a simplification, and we will maybe also cover later if we have it as a distributed load, what changes then. So, all right, single force calculated by the mass times the gravitational vector of the Earth. Gravitational acceleration is this. Yeah, and then you have the Young's module. Maybe I should include that. Yeah, but E is okay. Yeah, and A is just the half of the length. This is the E parameter here, which shows you where the force is acting, right? And now you can just calculate by this equation how much you have your maximum deflection on the beam. And this is the value we will be then comparing to the finite element method. Now, but we want to have that automated. So we want to have a script later on where we can just put in some input parameters and just let it run through. And this is, yeah, the interesting part of this topic, because I think you have seen those simple models being built up in Hypermesh quite some time, also on this channel, and it's really interesting to just compare, for example, 1D elements to 2D or 3D elements. But I want to take this approach to automate it in this video. So let's start. Yeah, let's jump into Hypermesh. I have prepared a notepad here because we want to have the equation at TCL commands. And let me just quickly jump into my browser, change my, right, that suits better. All right, so we have Hypermesh here. Now, to set up our code, we want to go to our documents folder, which is documents, and then you have command TCL. This is usually the file we're looking for. This will record all the commands we're doing right here. So I will just simply delete this file, or just delete the contents and save it. Oh no, that's not possible. Maybe I cannot delete it as well. Just wanted to have a clean start. Yeah, it's not possible. All right, doesn't matter. So we let's try it. Let's try it with the admin rights. No, cannot be saved. So no, I want to just open it. Those are our commands, and just scroll down to the bottom. This is where we're at. And now I want to build up the model, right? So simple terms, I have the values here for geometric values, the length, for example. Let's start with a simple length of 1000 millimeters and the diameter of 120. So this should be our base model, right? Yeah. Now I will just create the basic model here and have an eye on this, what changes here, and then copy the important parts onto a new file, right? So this is what I try to do. All right, So let's start. I want to create a node at 0, 0, and I want to create another one at 1000, 0, 0. Right, let's see what changes here. You can reload it here, but I know I once had a tool for that. But file reload should work as well. Oh, it doesn't work. What? Okay. Let's see if this changes when we draw a line. So lines from, well, we could do it also with that, like this. Is this not reflected here? No. So I'm guessing I have the wrong command TCL opened. I'm sorry about that. Just have to restart. Ah, this is the one from the last tutorial. No, and I will just restart it. Right. So for version reference, I'm using the 2021.2 version of Hypermesh, and I'm starting HyperWorks Desktop in a new layout. So you can also do that with the old layout, so this should not be a problem. And now let's see. Now I have a different command file, which is this one. And let's also go to the bottom. So how I like to start my models here is to delete the original. And there's a quick, there's a option. So this delete model will delete a model, right? So if you just input that here in the TCL console, it will ask you, do you wish to delete the current model, right? And yes, but I don't want to click that, so you can import or just use this command hm for Hypermesh underscore answer next, then a space and yes. So, and inputting this just deleted the model. Alright, so this is how I would like to start. Then you can see our commands reflected here. Now let's start. We wanted to do this with geom lines. Yeah, I want to have that with a line because you could do this with two nodes and one element, but I wanted to have multiple elements, and that's why I choose to have a line mesh. I think that's easier. So lines, and then we have here 1000. So it's like this, and let's see what this changed. So we have here line create straight, right? So this should be the command here. And I think what's the sign for comments? I think it's %. But I think we can do that here with languages TCL. Is this a comment? No. Alright, it's just like in Python, it's a hashtag. Alright. Create line. So we will have to be a little bit precise here. So I think delete old model, that's okay. And now we want to have variables. And for example, we have the variable L. And now I think it's a bit disappointing that I don't know this, but I think it's with the equal sign. No. Should be set, alright, no equal sign. Set L and then 1000. Right, this is okay. And now if I have a $L, this will get me the variable. Alright, so our command for having the line created, oops, having the line created was this, and here we want to include our L. So $L should create the line. So it will create it also in the basic, in the component, and if there's none, yeah, it's not so good. So I think we should make a basic model setup here. And let's do that first. So I will just delete the model once again and create all the stuff we need. So create, let's just refresh here the file that we know where we are. So here. And now create, let's start with the material. This will be the same every time, so don't bother with that too much. So in terms of variables, we can include this also later. So material 2100 for the Young's module and the Poisson ratio, and we also maybe want to include the density. Alright, next we want to create a property, and the property should be, I'm always wondering, is it pbeam or pbar? Let's stick with pbeam. They don't matter this much because they're the same thing. Then we want to have the material which we already created. I should have created that beam section before, and we cannot do that here, right? No. Let's leave that for now. And alright, that's about it. For the property, let's name the property differently. pbeam. Okay, and then finally we want to create a component. And this component should have the property pbeam and also material mat1. And we call that my component. Just to have it a little bit differently. Alright, so we have components, we have materials with a property. What we are missing is a beam section. Beam section. Can we do that here? Yes. So, beam section circle. And this should be a rod, which is perfectly fine, and the radius should be 60 millimeters because we want to have a diameter of 120. And now we can assign also the beam section to the property. Property pbeam. So the beam section should be the only one we have. Alright, now we did a lot of things here, right? And now I'm a little bit afraid to refresh it here, but yeah, so everything here, starting from here to the bottom, can be important. So I will copy that to here. Alright. Now excuse me for a minute, we'll be right back. Alright, I'm back. I just prepared some tea because it's not the same without it. So, cheers, I guess. Alright, where were we? We have here the, oops. That sounds good. Okay, we had here the basic model setup, and you see all those start end node history. You can all forget about this. This is just for your convenience, that you can see what happens here. And this is not important, so we can change that. Just had to plug my keyboard in because battery is running low. Okay, so we delete all those. So this is all rubbish. Or not rubbish, but it's not necessary for us. Right. At the beginning it's rather helpful because when you don't know what the code is doing, those histories will tell you what does what in the code. And we will declutter this in a sec. So all those. And you all, for sure, you can automate this as well. So for example, you have maybe a parser which runs through that file maybe also in real time. And if it starts with start node end history and or end node history, you can delete it. But I'm lazy in this case and did not do that. Alright. That's also a little bit a gamble sometimes, because you have to decide if it's important or not. For example, this merge history state, but in doubt, just leave it in there. Alright, so it's not so much lines. Now, for example here, this set value comp, my comp, this can be totally left out, because you have this command which creates a component and you have to give a name here. And now if you just give the name right here, you don't have to have to do it later on to update it. And well, there can be I think there can be a lot of those type of commands where you can include it here. For example, here the top of face color is done twice. I don't know why, but I don't think it's that important, and also we really don't care about the top face color too much. So I will just delete the things I think which are not necessary. But I will be gentle here, because I don't want to screw it up and have to record it once again. So, alright. Now let's see. This is just a basic model setup, right? It does not really do anything which we want to influence with our variables, I think. Or is it? Yeah, it is. The diameter here. It's not the diameter, it's the radius. You have to be careful about this. So, let's see. Set diameter 120. And here comes the trick. If you want to do something like an equation here, you have to use the brackets. I think you have to type an equation, or EQ. No. Eval? I think eval. For evaluate, because the way the interpreter interprets the language here is which part of the line is executed first, and if you want to have a equation in there, you want to have the value of this equation being done in the code before the rest of the line. So eval shows you that the content in the bracket is being evaluated before the rest of the line. So this is it, and now let's see, it's diameter divided by 2. And I will do the double here, because I don't know if it's in TCL if it's a problem, but in Python or Java it really is, because you have integer division. And for example, if you have something like not even numbers, right, and divided by 2, it will have something behind the decimal point, and this will get left out if it's an integer division. But rather include a point or decimal point in the division. So, yeah, this happened to me quite often. Alright, I think this is the only thing we want to change here, right? All the other things can stay the same. And after that, we want to create our line. And now let's see. The good thing is you can always Control A, Control C for copy of everything, and maybe save it. Save it is a good thing. Let's save it here. Script rot YouTube. Yeah, you can Control A, Control C to copy everything. Then you just paste it in here. And if everything works, last command you always have to put an extra enter here, because it has not a new line. Invalid command name 100 divided by 2. It's not so good. I think there's a different, it should be called a little bit different. Let's see. Just open up a browser. TCL equation. I think it was expression. It's not eval, it's expr for expression. Okay, once again. And now we have everything set up. So blue codes here, like the ones, those are correct. So those are perfectly fine. If you have a red, like here we had, it says your invalid command name, and then if you click on it, you can see the code where you had that error. Alright, so, but as of the look of things, it should work. So we have our beam section, and let's see if 60 is in there. Yes. So this worked. Now we can continue. So we should have a line here, which is in the first component. Yes. And now we can, well, we have the basic model set up, right? So we just want to have the line mesh. So first thing, line mesh, and the boundary condition, load step, and that stuff. And that's about it. It's not that complicated, right? All right. Let's do the line mesh. So we are at the state of the end of our script. So we want to have here the line mesh. And we will do it like this, 1D, and there should be line mesh, and then we select the line. This will be tricky. Well, if you want to do it right, it's tricky, but you have an element size. Let's make it something different that I can recognize it. And property, we will actually not be using a property too much, right? Because we will be adding the elements to the line component, and the line component has a property assigned which has a beam section, so it's everything defined, so we don't have to assign a property directly to the elements. But the element config should be beam, in this case bar 2. This is a little bit yeah, complicated, but in 1D element types you can see that for bars you have C-beam elements. And so I suspect that if we create a line mesh with bar 2 elements, there's no beam here, that it will in fact create C-beam elements. Let's see about that. Alright, so I'm just refreshing our command TCL that I know where we at. Yeah, because we did the element type, it just put up everything because, yeah, we didn't change anything, but just in case it does this. Alright, so this has nothing to do with the line mesh command. So I'm selecting the line, we have bar 2, no property, we have elements to line component. Auto is the orientation. Yeah, auto is fine, it's round. Yeah. How bad could it be, right? And mesh. And return. And return. So we have elements. And now let's see what the script did here. So everything here we will put into our little command file. So element size set. This is our mesh size. Let's put in a variable called mesh size. Let's do it like this. We could even make it maybe we want to do that depending on the length. L divided by 100, for example. Could be it. So we have a mesh size here, then create mark lines 1 1. This works here because we have just created one line, and the line component is then with the ID. Not the line component. The line itself has the ID 1. But it's not error prone. If you have two lines or separated lines later on, this will definitely fail. Then we have some prepare data, which I would have to look into the help to see what it really does. But for this case, we will not bother with it. Then we have to save data. And then all the color options. I think we can all leave that. Those are... So this vector, this is interesting. Because normally if you have a cross-section which is not symmetric, for example, a Y or a W cross-section, or a U cross-section, or T cross-section, like this. it makes a difference if it's like this or this or this or this. It's, yeah, you have to give a orientation vector. And it's a little bit strange because the vector here is the same as the vector in which the direction of the beam is pointing. So it would be completely wrong if this is that vector. But I think Hypermesh has arrow checks in this and will do that automatically correct. But to be fair, we have to check that, right? So if you click on this and then on 1D and 3D beams, 1D and 3D beams, you can see that it actually worked. Let's shade that you see that a little bit better. So, see, this works. That's why we will leave it here. Now comes the fun part, right? So you can, for example, change that to 1/10 of the length and just Control A, TCL, Control V. Oh, can't read mesh size, not such variable. Oh. He did not like that. Why did he not like that? Invalid bareword 1 in expression. Ah, this is not a 1, it's a L, and I forgot the $sign. Okay, just once again. And that's the beauty of coding in this case. You just can run it once again, and you can see the different outcomes. In this case, I would have suspected less elements. But I think in this case we did not catch everything here. Because I think this thing here, the number of elements. I'm not 100% sure. But I'm pretty sure because 1000 divided by 9. Let's see. You just make it like this. Expression of mesh size. Or rather, length divided by mesh size. Let's see. Suspect that. So if you want to do it properly, you would go into the help and try to understand every part of it. But I think this worked. No, it did not. So now let's do it properly, right? We can always go to the help, which will then open up in a browser. And most times you're lucky with just searching for the command name. Alright, now we were looking for second parameter. Density. The element density to use for this segment. Mesh lines 15 and 18 with a 30-degree break angle with 3 elements in the first segment and 2 elements in the second. So this is the number of elements. Yeah, the problem here is, I think this should be an integer value. This should be an integer value. So we have to give that an integer value. Let's see. So the problem is this expression yielded in something like 10.0. And this is not good. Okay. TCL convert to integer. So this is possible. Sure. Integer. Much better modification would be to put it all into one command. Yeah, let's see if that works. We have expression, and then we want to have an integer value of this division. Hopefully that works. I don't think it did. Did it? No, I don't think so. No. What? What happened? Oh, it did work. It did work. Yes. So I was just wondering because I did not see the C beam, and yellow is maybe a little bit stupid of a color. Let's put something darker. But it worked. So this is not the thing, but here. Yeah, too dark. Too dark. By the way, Dark, fantastic series. I'm bragging all my friends about it because I'm in love with that series so much. I watched it, I think, 4 times. And still have to use the family tree for the season 3. But it's an awesome series. Alright, yeah, so this worked. We'll leave it at that. Let's change the parameters. Let's try fiddle around with it a little bit. So for example, let's say we want to have the mesh size, the length divided by 56. So there will be definitely be no even number coming out of that one, I guessing. Yeah. Let's see. Control A, Control C, Control V, and you are up for a little bit fun. So we expect to see a difference. Yeah, we do. We do. That's good. Good news. Let's check it just one more for completeness. Yes. And those should be 56 elements. No. 1000 divided by 56 and that rounded to the next integer. Let's see what that is. Because we only believe what we see. So 1000 divided by 56 should be... No. This is the element, the mesh size. This is 17.85. This should be the mesh size. And we can check that. If you just go to... I'm a little bit struggling with... just get used to the new visualization tool. So if you just measure the distance between 2 nodes, 17.857. I closed the calculator, but I think that was correct. Alright, now that's a good thing. So what's missing? If we say that's all good, we can now go and put in the boundary conditions. And here comes the fun part, right? Because depending on the mesh size, we don't know, really don't know, how to put the force in the middle of the beam. This is what we should have done in the first place. And this is also a good thing to see here, because now those commands will not work really. And as I saw here, oh, and I totally forgot to switch the displays. I'm sorry about that. So you just have to believe me that this all worked and that this was correct what I told you here. I'm sorry, but the thing is, so we can now put in different mesh sizes, so this works all fine. But the force in the middle, this is kind of a bummer, because we would have to separate the lines, right? We have to split the lines. And that's a bit of yeah, let's do it. So I will just delete all the elements. Now we want to split this line. So we want to line edit, split plane, for example. Split at plane. So we want to split this line at a plane which has a normal vector pointing into the x direction, and the coordinates would be the half of the length, and the length was 1000, so 500 for x is here correct. That looks good. And now return and split. I think that worked. Yeah, we have 2 lines now. Now the thing is, in our commands, whoops, in our commands we will now search for the split operation. So this is rather easy. So we include this create mark lines 1 1, create plane, blah blah blah, line split a plane. That's all good. And this should be right after the creation of the line. And also there's a trick here. I think you can also create a mark which was created before with -1 or something like that. You have to look it up if you really want to make it more error prone. But just be remembered that this, or reminded that this is possible. Now this would be a expression of the length, not dollar, not percentage, sorry, $L divided by 2. So this should give 500, and double values here not a problem. So let's split it here. But now it's interesting because we have 2 lines here. And as we saw here, you have the line save mesh parameters for 2 lines here. Let's see how this goes. I will just make it once again. Line mesh. Select both lines. So 2 lines added. Element size is okay. No property, bar 2, mesh. Return. Let's see how this goes. And so you can also understand the behavior of Hypermesh a little bit more. So you see here, this comes only 1 time, and now you have 2 lines. Oh boy. So the first line was ID 1. Now you split the line and you have ID 2 and 3. So this will be a dirty coding style for sure. You could do something like displayed or all, then you have all, but then you would have to do something about line mesh parameters to do a loop over that, which would be the fine solution, but I will not go into that because that's a little bit longer. So we will just include it like this. This is hard coded. So if you change anything in the above code, you have to adapt. And I forgot to change the monitor once again. Stupid me. You have to change those values as well. So what I was just showing is in the command here, you see that the create lines happens now differently. You have for 2 lines beginning with index 0 and then index 1, you have 2 parameters, which will be the same parameters for us. But we have this here, which changes. We had here just 1 1, and 1 1 means you have just select the line with the ID 1. But now we have 2 and 3, and this is the hard coded part, because if you change something here, maybe split it once more, 2 and 3 means something different. So it's not, yeah, it's not that easy. But alright, we will do it like this, and I think this is fine for now. So selecting 2 and 3, now we have to include a what? Line save parameters 0. Alright, here 0 and 1. And I think this is the same thing. Yeah, because we have to split it in equal lengths, right? But this could also change, right? This could change. This could change. Maybe we want to include that right here from the start. Because, yeah. See, Here the problem begins. You don't know really what to include, and you have to plan in advance. So for example, if I want to include to be able to change the parameter here, A, which is the value where the force is acting, later on, then I want to also change this one, right? So this X value is A. So here, this X value is A, where you split it. Let's just make a new variable, A. And this variable here happens to be L divided by 2. So this works now. But if I want to change that later on and maybe put, for example, set A 300, then you would be splitting the lines not equally. And the counts of elements in the first line would be different from the counts of elements in the second line. So, how to account for that? A divided by L is the fraction for the first line. Let me think about this. So if you have A divided by L times L divided by mesh size. Yeah, no. It's easier. It's a lot easier. You can just do A divided by mesh size because the first line is exactly A long. And the other one is exactly L minus A long. So you can do L minus A divided by mesh size. Should work. We will try it out. Now let's see if this works. So the basic one. And go into the TCL console. And we had a problem. Not such a variable. Oh, forgot the expression here. What? I think my Hypermesh crashed. Yeah, it can happen. Alright, let's close it. And open it. There's also one thing of the beauty of coding. So you don't lose your progress because you're working always in the sense that you can recreate it on a key press or just insert some code in here. And if you had a crash in real life, so without that you do the coding stuff, you maybe had to go into the command TCL and execute it and hope for the best. Or you have to redo it. And yeah, so this is also part of why I like this style. So now we can see we have the lines splitted equally, I guess. So this is the first line, this is the second line. And from the looks of things, it looks that we have the same density overall. So that makes sense, this is okay. Now if we want to change the parameter A to something different, for example 300, and let's see what happens now. Oops, that was not good. Let's see. On the first looks, it seems that we have the same density overall, and that would be a good indicator. Yeah, this works. And did the line split work as well? Where are my panels? Yeah, this worked as well. Great. Great. All right, so we have this set. Now we can go and advance to our SPC or boundary condition. We call it load step. Okay, I hope this is still the same. I'm not sure. No, it's not. It's not. So I close this and open the second one again, because we closed the program and reopened it, and so the file changed. Alright, now let's see. We want to create a load collector, which is called SPC. Has no card image, analyzes constraints. I want to do that on points. Can I select a point here? Null points found, or 0 points found. Okay, this is not possible. Because I really would not like to do it on a node, because the node changes with every... Yeah, but we don't have another option. Let me try once again with the components, and I want to not display the mesh. And I think this should be a point, isn't it? No. No. Cannot put line ends on that. Alright, that makes it a little bit difficult. So we have to work with nodes. So we will include those two nodes. Or rather one node first. And those node will get, this node will get all the DOFs set to 0. So it means it cannot move in any direction, which is this boundary condition right here. So it cannot move in any direction. This is the fixed bearing. And this one is the loose bearing, so this can move. So let's create it first here. And then select the second node here and remove the X DOF. DOF1 means translation in X, and if we don't check it here, it means this node can be moved freely along this axis. Yeah, alright, create this as well. Now the fun part begins, because how to select the nodes? If you have the ID, yeah, for sure, but if you don't have the ID, and we don't really, then it gets a little bit more complicated. And yeah, so what we did here, this is the creation of the constraints. And where did we create okay, I have to see. Somewhere I should have created a load collector. Alright. Haha, I did it a bunch of times. This should be it, right? Yeah. So here we created a load collector. Okay. So create a load collector and rename it here in SPC, so we can skip that command. This clear mark is always a good idea, so you don't have any problem. But we did not select it, so forget about it. Create entity load calls, include ID 0, name SPC. So this is done. And now we have the creation of the SPCs. Oh Lord. Alright, copy that over. Let's maybe also put it here as constraints. Now, create mark nodes 1. Yeah, you see the node idea. That's not good. And then you create the entity on curve, and here you can see which DOFs are fixed and which are not. We can look that up in the help, but you can see here the minus 9999999. Those are free DOFs. And here you can see X, Y, Z translational direction is fixed. and then the rotational directions are free. This is the fixed bearing. And here you can see the X direction is fixed, is free as well. So this is the loose bearing. Okay. So the only problem I have are those two lines. This line and this line. Because those can change. And there's a trick to create to create a selection. So we want to create a selection of nodes. Yeah, let me look that up. This is one of the most important commands, and let's look that up. Create mark. Okay. Let's see. Well, I have to have the real create mark command. There's also hm underscore create mark. I guess. I think there is. Maybe this is, yeah, this is the same command, but alright. So what I wanted to show you here is we wanted to create a mark on the nodes. We know the geometric position of those, and we want to do this in this case by box. So this will be the command I will be using. So shift that over. So I will just use here hm create mark, then nodes, because that's the entity type, then 1, because you can have different marks and the 1 is this first one. Create mark nodes 1, and now this fun begins. So by box means where we have our box, and the box is just a bounding box around all the nodes we want to select. And so we will create a tiny little bounding box around this node. So we can only select this. And therefore we need a tolerance value. So for example, set tolerance. I don't want to call it tol, because tol is used later. Let's just call it delta, because it's a difference. And I also want to have a short name because we will use it a lot. So set delta 0.1. Okay. Okay, I can have it here. So set delta 0.1, and now we want to use it here. And you see, we have to first pick x0, y0, z0, and then x1, y1, c1. I'm always getting confused with z and c, but I will call it c now. Now, system location contained all tolerance should be pretty straightforward. So I'm looking at the help right now, so you don't. System, the ID of the local coordinate system, so 0, 100%, because we know to use the global system. Location, then is defined, relative valid values are inside, outside. So location would be inside. Contained, a flag. Yeah, this is if you have to, for example, select a component and your bounding box only touches it, this should be 0, or except, or the other way around, if you want to have the complete solid, only then select it. If you have the bounding box completely around it, then you have to use 1. Doesn't matter for us, so we can have it 0. Then we have all flag that indicates whether all entities. Yeah, all is okay. So all entities would be a 1 and tolerance to use. This is 0. Okay, now we are left with those values. And this should be straightforward for this location. But for each, we have to put in an expression. So, expression 0, because that's the starting point, minus delta. Then y, it's the same thing, right? Y is also 0 and z is also 0. So 0, 0, 0 and always going delta and minus. So it's, for example, minus 0, 1, minus 0, 1, minus 0, 1. And now we have to go to plus 0, 1, plus 0, 1, plus 0, 1. So this is, this case, the same thing for here. But we have to do pluses here. Plus, and again, and the final time. Alright, let's see if that works. If we just use it here, can't read delta, okay. Set delta 0.1. One node added, so it seems to work. And we have to use the same thing here for this. But here, instead of 0, we have to use delta L for, no, not the delta, $L for X coordination, here and here. Because our bounding box, not only here and here, but yeah, only here and here. Because we want to create a bounding box around this node. And this node is located at L, 0, 0. And L minus delta. Now Y would be 0 minus delta and C also 0 minus delta. That seems legit. Let's see. You can always go Control C and Control V and see what this does. By the looks of things, it worked. So this is rather a fiddly part, but it's worth the effort, because now if you change L, it will be correct. Alright, so the constraints are set, and now we have to do the same thing for the force. So let's go into the model, create another load collector, name that force, no card image, close it, and then just create a force, because I will not bother too much with the coordinates or the nodes too much, because we will change that. So 100 newtons, for example, in minus y direction should do the trick. Okay, I created the force. I'm now going back to my command TCL, reload it, and see where this went. So this is this, and here we have the creation of the load collector. So this is the part where we want to copy that over here. That's the force. So we create this load collector named force. Can delete the annotation history. This is also not necessary anymore, because we have the name up here. This is also not necessary. Here again, we want to do something like this again. But here, in this case, L is A, because this is where the force will be at. That should be it. Now we have the force value. Let's see. Let's make the force as a parameter. It really doesn't matter too much if it's positive or negative. So we'll just use it here. So let the force be with you. Sorry. Bad joke. Let's let the force be, in this case, 865 newtons. Is that correct? It will be 86 kilos. Yeah, should be good. 120, 1 meter long. Yeah, could be it. So 865. Let's just quickly go back to here. So set force 865.4. Okay, so we have the force here. And now here is a bit tricky. So we have the magnitude here, and this is the direction of the force. Well, we will just replace this. So here's a force, and here as well. You can look all the different aspects of this command in the help if you're interested. But this should do the trick, and I will also include the minus up here, so that this is set. And that's about it for the forces. Now, the load step. Yeah. Let's do the load step up here. So the load step is combining forces and SPC boundary conditions. The load step, right? So analyze this load step, and we just create one. And have an SPC and a load collector. And that's about it. Let's see what this yielded in the command file. So this is the part. Here, up to here. You'll see the history state is useful. So you see the load step creation begins here, because I would have skipped that because I saw, alright, create a load step here. But those 3 commands are necessary, that the SPC and loads collector get assigned here. Because you can see here it creates a mark on 2 load collectors, and then it refers to that again. I'm not quite sure about that, but those could also be IDs, and I think rather those are IDs than positions in the list here. But yeah, rather be safe than sorry, so we include everything, and I think we cannot change here anything, so this should be good. Now comes the part. But definitely we want to have reaction forces also. So this will be in the control cards. And the control cards we have to define here. Let me see. My monitor's right? Yes. Okay. Analyzes. Control cards. Then we have here the global output request. I think so. And then SPC F. Okay. Let's just leave it with the standard here. Look back what the command yielded. Yeah. If you update control cards, it's a bit much, because it updates everything always. But we won't bother with it. We will just include it here. Could try to find which is the global output request, but this is rather unnecessary. So here you have this could be it, yeah, because you have a one set here. Alright. This should be it. So let's test it once again if it's still working. No reds. Alright, and we have our value here. And this should be the point where all lines are separated, right? Let's see. Can go and check that with line edit. See the line here? Yeah, exactly. So this worked perfectly. Alright. Now, let's test it. We will set the diameter to 120, the A parameter to 500, which is 1/2 of the length. The force is matching with my Excel sheet. We will just include it here. Build a model. Run the model. Hope for the best. So, panels. Let's see where we put that on the desktop. Rod. Tidy up. This would be 120 millimeter, 1000. Let's put in L 1000 so you can see what I'm doing. L 1000 and A 500.FEM. Maybe I want to do a parameter study afterwards, right? Now, let's run it and hope that I did not forget anything critical. Unfortunately, it will not take that long because, yeah, the calculation machines are fast. And it's an easy model, right? Now, you see the result already here. The maximum displacement is 0.0086. I will include that here in my Excel sheet. And we have a difference. But the problem is here maybe this thing. Yeah, so a 3% difference, which is quite a lot, I think. This is quite a lot. It's reasonable. But I'm not quite sure. It has nothing to do with this, I think. So we can see a little bit better. Well, maybe I shouldn't be not that harsh with the FEM. But I would suppose, yeah, I would have expected that it would be a little bit better. Let's make a study. Let's check it because it's important that you check that. So the first thing I would check is the moment of inertia. We have a value here. How does this compare to the beam section? Beam section would suggest it's not so easy to find actually. So it's somewhere here. But you can see there's a lot of different area. This is it. 10178.760.19. So mine is a little bit. Seems that it has here a difference. So mine is a little bit off. Let's see. Oh no, it's just a thing for me because I was wondering. 197631. Yeah, it's almost exactly the same. Well, maybe I should be not so harsh. Let's try for a different setup with a more deflection. For example, let's increase the diameter. No, let's decrease the diameter to 60. And let's increase the length to 5 meters. So now we have a decent deflection, right? Now, I know where the no, I don't know. I just was thinking that the load is not at the exact same point, but we split at the line, so no, that's not it. All right, so 60, 5 meter long. We can include it here. Length 5000. Let's use the equation here. It's the middle, and this was decreased to 60. And mesh size, maybe let's say we have 100 elements. That's too much, but 10 elements, 100. Let's say 100. And the force would be, we could also include that as a, maybe this was the problem. Because I did not include all the decimal points here. Yeah, that was a problem for sure. I will copy just the force here for the new load case. Let's see if this is better. Okay, include it again. Now it's showing into the direction of y. Really don't know why. Ah, yeah, I know why, because I did not include it here. But it's fine, it's fine. Less distraction for me by copying the force value or displacement value into the Excel sheet. So let's run it. It's a bit off. It's a bit off. It's not by much. It's a bit off. But it's not even a percent, but yeah. So this is the range I would suppose to be in. So between 0 and 0.7%, something like that. But you can see if you have more displacement, you have less effect of rounding off errors and stuff like that. So this could be an explanation. And also I did not put in the force correctly. But we could also put the force in equation form here. Let's do that. Let's do a final check. So the force I calculated by the mass times the acceleration of the Earth, gravitational acceleration. Now that will be a little bit of a hurdle, but let's see how far we get. So set mass. No, the density does not, because the density is, I think, a little bit off in my Excel sheet, but this is not the point. So density is set to, it's also rounding off errors here. I'm not sure. Not quite sure how to tackle this. We'll just use it the same thing as here. So set density. This is in square millimeters, in tons per cubic millimeters. So density is this. And now we want to calculate the volume. So now I will be thrilled to see how to do pi here. But this should be an option. TCL pi. Switch monitors so that you can see what I'm doing here. Yeah. Alright, I think we will have, and again, we have rounding errors. But yeah, I think that's enough, right? So let's define pi here. I know this is not really appropriate, beautiful, but it serves the trick. So volume is an expression of pi times diameter, and now the next thing, I'm not sure how to do. TCL, the power. So TCL. Exponent. Here, that's the exact thing I'm looking for. We have to define that? Oh no, really? Oh god. No, there's a power. Yeah. So this should be the base. Alright. Let's see if that works. So pi times power. And here diameter, comma 4. So no, squared. So pi times d squared divided by 4 times L. Should be it. Mass would be volume times density. And the force then would be mass times stupid now. Yeah, gravitational acceleration. Alright, and we have to use expressions here. Alright. Let's see if that works. Alright. Wrong arguments. Okay. Equal sign again. Again. Can't read diameter. Have I spelled it wrong? Yeah, diameter. So, no. So, let's compare the forces. My Excel sheet says it has a force of, yeah, 7.477. And let's run that. Don't bother with it too much, just run it. This is wrong, Ray. By the way, we forgot to update it. What did it tell me here? Oh, right. Okay. So 21.0922. Yeah, it's the same value we got earlier. So it's the same thing here. But I think that's fine. So a model check is okay. But what else could we check, right? So it's not stopping here. We can go into the hyperview. Oh, and that will be a challenge for me because I don't know how to do it in the new version. But we will see if I'm able to. So what I wanted to look is the reaction forces, because we can compare that to the analytical values here. So we have, yeah. So if A is a half of L, so 0.5 divided by L means half of the force. Half of the force, yeah, it's that what your intuition says as well, right? So if you have a force in the middle acting here, and you have two bearings which support it, then those supports will share the weight in equal ratios. So half, 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 half. All right. Yeah, let's see if that's the case. So if you are here and our force was 1081, we would expect to see around 540.5 newtons on each side. And we did export or output request the support forces, SPC forces. Now, new version, always a... we have contour here. That's good. Now we can go for SPC forces, apply. And now we can see 440.9, which is rather accurate. Now let's see, where is the measure tool? Sorry about that, because I'm used to work with the old layout, and there you have the measure group and stuff like that. But you have a contour plot, that's okay. Vector, tensor, deformation, ISO, results. No, system, table could be. Table is okay. So we want to have the nodal contour. Contour, yeah. So we just click on that and on that. Now, those are the two end nodes, and those share the same time, the same forces, and those are that's what we expected, right? So this is also a sanity check of your model, and I think it's time to conclude this video. So what to recap, what we did here was we created a routine for creation of different setups for problems like these. So we have a bar with two bearings which do not support the moment, but just translational is fixed. And we can also change where the force is acting. We can change the mesh size. Right now the force is defined as the self weight, but this could change. You can put into the force whatever you would like as a parameter here, and everything else beneath runs smoothly. And again, and you can change model sizes and mesh sizes and compare it. And I think that's a that's a basic start. I think yeah, this is a basic start where you can work your way up and try to understand what each parameter does. And also, I think the main reason why I did a video like this, which is a little bit longer, and you can also see me doing some stupid stuff in here and errors. You can see how I cope with them and how I search for the definition and jump between the command TCL and my own script. And at the end, I have something like this, which is more or less a template for problems like this, and I can save it, can use it later. This can be improved for sure, but I think it's a good starting point for you to just make your own experiences. And I would encourage you to do work in the style of this, because yeah, you can see the benefits. You can easily re-execute those lines of code. You get an understanding of the problems here, and yeah. So for me, it's a great tool available in Hypermesh, and I use it quite often. So without further ado, thanks for watching. If you could leave a thumbs up, a subscription, or anything else, a comment on this video, I would be happy. And I'll see you guys in the next one. Goodbye, and thanks for watching.